Good afternoon. My name is Dr. Irina Rакитянская, and today we start our first lecture of general chemistry. Today's topic is atomic structure. Before talking about atomic structure, it's necessary to say some words about the history of this question. First of all, in the beginning of 20th century, the electron was found out. And it was the actual question, where is the place of electron in the atom? Thomson thought that electrons are collected in the center of atom, making big negative charge, and positive charges are distributed in the atom like plums in pudding, and this model was called plum pudding model. After that, the colleague of Thomson, Rutherford, tried to prove this plum pudding model, and he was surprised about the results of his experiment, which are not agree with this plum pudding model. And he made his own model, which is basis of our modern imagination about the nature of atom. According to the model of Rutherford planetary model, in the center of atom we can see positively charged nucleus. And negatively charged electrons surround it. All the electrons have their own orbitals, like orbits of the planets. Of course, nowadays we have a more complicated model of atomic structure, but this structure is enough for understanding of the nature of elements necessary for understanding the chemical nature, for chemical properties of the elements. Let's say some words about the nucleus. Nucleus consists of two types of particles: protons, which have positive charge, and neutrons without charge. Protons and neutrons have equal masses. Mass of protons is equal to 167 times 10 negative 27 kilograms, and mass of neutrons is the same, 1.67 times 10 negative 27 kilograms. At the same time, mass of electron is equal to 9.11 times 10 negative 31 kilogram. And we can see that mass of electron is much less than the mass of protons and neutrons. Hence, counting the mass of atom, we can neglect this value. And we can count that mass of atom is collected in the mass of nucleus, and mass of nucleus, it is the mass of protons and neutrons in its content. Of course, you can see these numbers is not comfortable to be counted, to be used in our practice. And for counting atomic masses, for counting the mass of proton and neutron, it's more comfortable to use another unit, atomic mass unit, AMU. atomic mass unit is equal to 1/12 of the mass of carbon atom. Why it was necessary to do, we'll discuss later in the following lectures. The structure of nucleus and the amount of protons in the nucleus is very important for understanding the nature of atom and for understanding the chemical properties of the elements. Number of protons shows the identity of this certain element. Look, in the periodic table, all the elements are placed according to the increasing their charge of the nucleus. And the first element, hydrogen, has only one proton. It means that its nucleus has charge +1. The next element, helium, has already 2 protons. And its nucleus has charge +2. So we can say that number of protons in the nucleus shows the identity of this element. If we have the atom with 5 protons, we can be absolutely sure that it is boron, but not beryllium or carbon, because beryllium has 4 protons in its nucleus and carbon 6 nucleus. How can we know the number of protons in the nucleus? It's easy. Just look at the periodic number of the element in the periodic table. Hydrogen 1, carbon 6, for example, scandium 21. Periodic number shows the number of protons. At the same time, you understand, as far as all the atoms are neutral, it means that number of protons is equal to the number of electrons. So we can say that in the atom of hydrogen, there are 1 proton and 1 electron. It's easy to understand. Number of protons is equal to the number of electrons in neutral atom. Another question: how can we know the number of neutrons? You can see that only protons and neutrons give the mass of the atom. So, knowing the atomic mass, we can calculate number of neutron if we know that mass of proton is equal to 1 AMU and mass of neutron is equal to 1 AMU also. Let's consider the example of, for example, silicon. From the periodic table, you can see that the periodic number of silicon is 14. The atomic mass is 28 atomic mass units. And we can calculate for silicon number of neutrons equal to the atomic mass minus number of protons. Atomic mass is equal to 28, number of protons 14, and we can find that amount of neutrons is equal to 14 for silicon. Yes, sometimes number of protons is equal to the number of neutrons, but it's not in any case. Many elements have different numbers of protons and neutrons. Let's consider beryllium. Its atomic mass is 9. Its periodic number is 4. And you can count easy in your mind that number of neutrons is equal to 5, not equal to the number of protons. There can be the situation when the atoms of one element have different number of neutrons. Hence, they have different atomic masses because of different of number of neutrons in their nucleus. For example, chlorine, Cl, exists as chlorine 35 and chlorine 37 because some atoms of chlorine has 35 minus periodic number of chlorine is 17. 17 equal to 18, correct? And another type, 35 minus 7 minus 17 equal to 20. These atoms of the same element which have different number of neutrons in their nucleus are called isotopes. If you pay attention to the atomic masses of all the elements, you can see that they are not integer. For example, sodium 22.99, boron 10.811. It means that these elements exist as different isotopes. So, what is the main idea for this point? We need to understand that number of protons shows the chemical identity of the element. The next important question dealing with the atomic structure is the distribution of the electrons on the electron orbitals. It's necessary to understand that electrons are waves and particles at the same time. And this nature of the electron gives different interesting properties. For example, it is not possible to show the position of the electron in the atom and its impulse at the same time. Electron is involved in the constant motion in the atom. And different electrons with different energies are distributed differently in the atom. The full distribution and the full position of the certain electron in the atom can be described by Schrödinger equation. But mathematically it can be solved only for simple atoms like hydrogen or helium. For more complex atoms, we have no possibilities to solve it mathematically. But we can describe the position of the electrons using 4 quantum numbers. The first quantum number, marked as n, is main quantum number or principal quantum number. Quantum number. It can take only integer values. N can be equal to 1, 2, 3, and so on, but not 0, not 1.5. It shows the level on which the certain electron exists. The principal quantum number for any element can be found from the periodic table. It's equal to the number of periods. Also, principal quantum number shows how many levels are filled by electrons. For example, sodium is placed in the third period. It means that only 3 levels, electron levels, are filled by electrons. In the atom of sodium there can be any amount of electron levels, but only 3 of them are filled. And of course, only 3 of them close to the nucleus are filled. The next quantum number, L, is an azimuthal quantum number. Azimuthal quantum number. The orbital meaning of azimuthal quantum number is subshell or sublevel. It can take the amounts from 0 to n-1. And it shows the the shape of the orbital which we can imagine in our mind. From school you know that azimuthal quantum number is expressed by the letters S, P, D, and F. Giving the numerical expression for azimuthal quantum number, we can say that in this expression S is equal to 0, P is equal to 1, D is equal to 2, and F is equal to 3. If we pay attention again for the principal quantum number, for the first level, we can find only one possibility of azimuthal quantum number, S. It means that on the first level, only S sublevel can exist. Only S subshell can exist. On the second level, if principal quantum number is equal to 2, there can be 2 possibilities. Azimuthal quantum number can be equal to 0 and S sublevel can exist, and 1. P sublevel can exist also on the second level. From school, I think you can imagine the shape of these orbitals. S orbital can be expressed as a sphere. P, dumbbell-shaped orbital. You can imagine it as, for example, balloon twisted around its axis. Twisted S orbital can be imagined as P orbital. D and F orbitals have very difficult shape, and unfortunately I can't express them here. I can't draw it here. The next, ML, magnetic quantum number. Magnetic quantum number. Magnetic quantum number can take the values from -L to +L. And the magnetic quantum number shows the orientation of the subshell in the space. For s orbital, only one orientation can exist, because the sphere is very symmetrical. But look at this Gantel-shaped p orbital. It is placed along the axis. In our world, we have a three-dimensional space, which can be expressed by three coordinates, three axes, x, y, and z. And three p orbitals are placed there as px, py, and pz orbitals. And the last quantum number, which shows the position of the electron in the atom, is a spin quantum number. Spin as rotation. Spin quantum number can take only two values, plus half or minus half. And it expresses the type of rotation, spin up or spin down. Why this quantum number is necessary, we'll discuss a little bit later. If we talk about the distribution of the electrons on the orbitals, we need to remember about three important principles. The first principle is of Bohr principle. Of Bohr principle. It tells us that firstly, the electron with the less sum of principal and azimuthal quantum number will be placed in the atom. Electron will take position with the lowest sum of principal and azimuthal quantum number. N plus L must be minimum. And according to this principle, we can show the order of filling of the orbitals in the atom. Of course, the first will be 1s. 1s, because it has 1 plus 0 equal to 1. On the first level, it's impossible to have something else, and we jump to the second level. 2s, sum is 2 plus 0 equal to 2. The next 2p, 2 plus 1 is equal to 3. It's okay. The next will be third period. 3s, totally 3. 3p, totally 4. 3 plus 1. The next 3d can be, but 3d is equal to 3 plus 2 equal to 5. At the same time, 4s sublevel is equal to 4 plus 0 and equal to 4. We can see that 4s must go on before 3d. 4s, 3d. After 3d, 4p sublevel will be filled. Let's think what will be after 4p. 4p sum is 5. 5s is 5 also. But 4d gives 6. So 5s period, sublevel, will go on before 4d. And so on. You can continue it by yourself, counting the sum total of principal and azimuthal quantum numbers. The next principle which we'll discuss is Pauli exclusion principle. According to this principle, at any orbital there can be only 2 electrons, maximum 2 electrons. Maybe 1, maybe 2, but not 3. And at the same time, these electrons must have opposite spins, plus half and minus half. S orbital with a sphere shape can exist with 2 electrons with opposite spins. At the same time, p sublevel consists of 3 p orbitals. Each of them can have 2 electrons, and totally p sublevel can have 6 electrons maximum. Let's try to fill the electron shells, electron levels and sublevels according to these 2 principles. Let's consider atom of carbon. Carbon has the charge of the nucleus equal to plus 6. It means that there are 6 electrons in its content. According to Aufbau principle, we fill the levels from the first. 1s, 2. On the s sublevel, there can be only 2 electrons. 2s, again 2. And 2p, also 2. Because totally we need to have 6 electrons in the carbon atom. If we consider the atom of noble gas, for example, neon, its periodic number is equal to 10, and the charge of the nucleus equal to plus 10, and number of electrons is also 10. Let's distribute these 10 electrons. 1s2, 2s2, 2p6. It means that for neon, the second level is completed. It contains the maximum number of electrons, 2 on the s sublevel and p on the p, and 6 on the p sublevel. If we consider the electronic structure of sodium, number 11, plus 11, it's already clear for you. 1s2, 2s2, 2p6, and we can't feel something else on the second level. The third period, the third level must be filled already. 3s1. 3s1 for sodium. And the third principle, which we need to take into attention when we consider the distribution of the electrons in the atom, is Hund's rule of maximum multiplicity. Hund's rule. Hund's rule of maximum multiplicity. The electrons distributed on the orbitals must have maximum parallel spins. It means that they tend to fill the orbitals singly, and only the singly filling the second electron can be installed in this structure. Let's consider the structure of nitrogen, number 7. Plus 7, 1s2, 2s2, 2p3. And let's show the distribution of the electrons using the quantum arrow in box model. In this model, the orbital will be expressed as a box. If sublevel has only one s orbital, it will be one box. And the electrons are expressed as arrows. Here we have two electrons with opposite spins, and we can draw arrow up and arrow down. 2s also with two electrons, arrow up and arrow down. If we consider p sublevel, which consists of 3 p orbitals, we show the triple box, in which 3 electrons will fill only its own box, 1, 2, and 3, to have the maximum value of parallel spin. According to these 3 principles, you can write the electronic distribution for any atom in the periodic table. Please make the home task. Write the electronic distribution for silicon, phosphorus, and chlorine by yourself, without my assistance.